Okay, in this lesson, we're in section 2 of chapter 7. We're going to talk about a specific type of polygon, a parallelogram. Okay, and our goal today is that we will be able to apply various properties of these parallelograms. Okay, and really practice that notation as we look for the different properties and applying the different properties. So, I apologize, this writing is like in the wrong spot, it looks like when we printed these books. So this should say, given the pairs of lines below are parallel, write in the measures of the remaining angles. So if we look at this set right here and it tells us that those are parallel, I'm going to mark those with parallel markings. So those two are parallel, these two are parallel. We know that if this upper left angle is 24 degrees, then the one across from it is also 24. I'm going to zoom in just a little bit. This would be 24 degrees. And because this transversal is cutting through those parallel lines, this is also 24 degrees, and this one is also 24 degrees, right? And we know because these are parallel that this other transversal is crossing at 24 degrees as well. So we can assume that all of these conclude, I should say, that are 24 degrees. Now remember, if we know that this one's 24 degrees and these two together, this 24 degrees and this other one, make a straight line, then we know that if we take 180 and we subtract 24, that will give us the rest of that straight line, because 180 is a straight line. So 180 subtract 24 leaves us with 156 degrees. So we know that this piece right here, this angle, would be 156 degrees, and its vertical angle, the one across from it, is also 156, and you'll notice that we're able to fill in all of these obtuse angles with 156. Now again, these are two sets of parallel lines, so that other transversal is also cutting at the same angles, so we'll label all of these as 156. Using that property and that understanding of angles and relationships, notice that on the inside we have this little polygon right here. This shape has 4 sides, and if I were to sort of copy and paste it over here on the right, I would have these same angles. So I have 156, 156, 24 degrees, and 24 degrees. Now parallelograms, right, have 2 sets of parallel sides, so I'm going to label these as parallel. And you'll notice these are the properties kind of that we're going to pull today, these relationships that we see. Remember, parallelograms, this one looks a little bit squished, but there's lots of different types of parallelograms or specific parallelograms. A rectangle, because it has 2 sets of parallel sides, is a parallelogram. It's a parallelogram whose angles are all 90 degrees, right? Even more specific than that, a square is a parallelogram. Oh, yikes. Pretend that's a square. Also 90 degrees. Other quadrilaterals, like this one, right, which is a trapezoid. Trapezoids only have 1 set of parallel lines. The other lines don't have to be parallel, so this one is not a parallelogram, even though it's still a quadrilateral because it has 4 sides. So to be a parallelogram, it needs the 2 sets of parallel sides, and it has to have both sets, okay? When you have 2 sets of parallel sides, these angle relationships always hold. So notice if you look at this inside our parallelogram, the opposite angles, they're always the same or congruent. In geometry, we say congruent. So down here with our properties, that's what I'm going to write in here. It says opposite angles in a parallelogram are, and we're going to say are equal. So I'm going to write that word because sometimes that helps for you to think. They're equal, or in other words, in geometry terms, they are congruent. Okay. And the notation we use for that, right? If I have this parallelogram off to the right, these are really small letters, so I'm going to write them a little bit bigger. That says A, this one says B, and C, and D. If I wanted to say that angle A is congruent to its opposite angle, so remember these ones would be congruent to angle C, then I use that squiggle with an equal sign. That means congruent. Okay, that means those two would be equal. So again, if I was given, say, angle A was 125 degrees, then I would know that this one over here also is 125 degrees. Those have to be the same. Okay, once we know that, the next one, if you look at the next property, it says adjacent. Adjacent means next to. So I'm going to write that right underneath it. Next to, not the number 2, but next to. I don't think that should have 2 O's. Okay, next to. Adjacent angles, or angles that are next to each other. So again, I'm going to draw some arrows up here in that one that we drew. 24 and 156. Remember, we used this idea that they add to 180 to find that. These ones are called supplementary. So supplementary, right? Or in other words, they add or sum to 180 degrees. So again, using this diagram and this parallelogram ABCD, if I know that this is 125, then I can find the angle measure of D, because I take 180 and I subtract 125, and that would give me what angle D would be equal to, right? So if we subtract that, we end up with 55. And then we would know, again, that B is also 55 degrees, so we can use that. Okay, so those are the angle properties. There's just those two. Either they're equal, because they're opposite, or the adjacent ones are supplementary. They add to 180. Opposite sides of a parallelogram. So opposite sides, because they are two sets of parallel sides, they cut each other and create equivalent pieces. So opposite sides are also going to be congruent to each other, right? You know, think about rectangles, all sorts of parallelograms. Opposite side lengths are always equal, or in other words, congruent. And again, if I'm going to write a side length, I would say, for example, AB, and I would put that squiggle line over the equal sign. Notice A to B is this top of the parallelogram. That would be equivalent, or the same length as D to C. So those two would be equal, so I could say D to C. Okay, so we know opposite sides are equal, and the last one, if we turn over the page, is diagonals of a parallelogram. So diagonals, remember, run from one vertice, so I'm going to start with A. I'm going to write this big again. A, and I would go all the way to C. So here's one, pretend that's a straight line. That's a diagonal. And my other diagonal could be, let's say, this one from D to B. So it goes here. If you look at those, you could ask yourself, now, are those the same length? Hopefully you answer no. You can see that from D to B, that's a longer distance than from A to C. Now, if it was a rectangle, right, so if it was like this, then those diagonals, they would be equal. They look like they are the same length. But this parallelogram squished down a little bit. But the cool thing about diagonals is they actually bisect each other. So we're going to use this term over here, bi, meaning two equal pieces. So bisect, so this is like they cut in half, or two equal pieces. So for example, if I'm over here on my diagram again, if I have D and I'm looking at from D to this middle, right? If that's a certain length, that would be the same length as from the middle over to B. So that would be the same. Same thing if I'm looking at A to the middle, that length would be equal to the middle out to C. So those two pieces would be equal. Okay, so we're going to do a couple examples of these. I'm going to do a few properties, and then I will come back to F, G, and H. So let's just think about the notation and the things that we just talked about. So if we look at this first example, you'll notice we have A, B, C, D, parallelogram, two sets of parallel sides. And if you look at this one, this says nothing about angles, so I don't really care about angles or diagonals, but this is talking about lengths. So if I'm trying to find these variable values on this one, and I know that m plus 3 is AB, that would be equal to DC. So all I do is say, well, I know that m plus 3 should equal D to C, which is 10. Those are opposite sides. Well, if I subtract this 3, I know that the value of m would be equal to 7. Okay, so using that property that opposite sides are congruent. Same thing here if with my n minus 8 and my 12, I know those are the same. So n minus 12 needs to equal, n minus 8, I apologize, needs to equal 12, so we add 8. and n would be equal to 20. Okay, so those are side length properties. If we look at this next one, Q, R, T, and S, I just want to talk about, if I was filling in as much as I could on this one, notice that from T to S, so down here, T to S, that's equal to 21. If that's 21, I also know Q to R is 21. So again, I'm just going to fill in some pieces that I can. I know that's 21. If I know this is 79 degrees right here, then its opposite angle is also 79 degrees. If I know that's 79 degrees, right, then I know this whole angle of T over here would be 180 subtract 79, because those have to add to 180 degrees. So we know that those are going to be supplementary, which means that angle T is 101. Oh, that's 100 degrees. Which also means angle R over here is 101. Now notice this other one has kind of a sneaky one. This diagonal right here is creating an angle of 31 right here, just this little guy. Now, if you think about if we were to create this into like a transversal, right? Remember, these are parallel lines. So think about if this extends just to create some parallel lines. And your transversal, if it kept going, this 31 degrees, right, would be equal to this little angle down here. I'm going to write it in this one right here would be equal to this one right here. So if that one's 31 up there, this little piece down here is also 31. Okay, all different things we can find. Using some of the notation, let's jump down to this third example with U, V, W, and X. On your assignment, again, you'll practice some with the notation. So it will say or ask, what would the length X, W equal? So you're going to come to your diagram, you're going to say, well, from X to W, that's this side right here, it should equal its opposite side. So that should be equal to UV, which is 16. Okay, it might ask, well, what is, oh, I need to give this, I'm going to call the middle T. What is X to T? Again, I look at the diagram, I find X, and I see that X to T is a piece or half of this diagonal. Well, if the other half is equal to 10, and we know that it cuts it in perfect 2 halves, this is also 10. So I could put 10 here. Okay, maybe we're asked to find W to U. So again, we find W, and it looks like U is this full diagonal. Well, we know if half the diagonal is 9, then the other half is also 9. So 9 plus 9, that would be a full length of 18. Okay, so there's some examples of using that notation. Let's look at these last 3 in our notes for this video, and then we'll talk about the parallelograms in the coordinate plane at another time. So looking at this first one, F is talking about diagonals. Again, I know that this piece of the diagonal up here, E to B, is equal to this piece. So we can set these two equal, and then it just allows us to solve. Once we set them equal, we go ahead and solve. 36 is equal to 4x squared. If we're solving, we divide by 4 on both sides, which gives us 9. And remember, if I undo a squared, I want to square root both sides. So in this case, x equals plus or minus 3. Now I always check to see if the negative solution actually works. If I put a negative 3 in here, that doesn't actually represent a length. It'll give me the same value out of 41, so it works. On example G, this one's now dealing with angles. So notice it doesn't say anything about the other parts of the parallelogram. And remember, in parallelograms, we know that opposite angles are equal. So again, as soon as I say that, then I say, okay, let me set them equal. That allows me to quickly solve. And I get x is equal to 87, and we subtract 29, we end up with 58. All right, last one here. H, we've got A, B, C, D. And notice there's some things we know. I'm going to zoom in just a little bit. In relation to this, we know that opposite angles are going to be equal, right? But if I set x equal to 2z, I'm going to have an x and a z, and I don't really know how to solve that. Same thing if I do these two. So the idea here is you want to choose the ones that have the same variable. So we have a z minus 15 and a 2z. And remember, angles that are next to each other, they add up to 180 degrees. So if we can figure out these ones, that'll help us find x and y. So we're going to take z minus 15 plus 2z, because these ones add to equal 180. From there, we just solve. So z plus 2z is 3z. We still have that minus 15. We're solving for z, so we add 15. 3z is equal to 195. Divide by 3. And z would be equal to 65. So we found the value of 65. Now it's very tempting to just say, okay, well, that one's 65, so then the opposite one's 65. But notice z is 65 degrees, or sorry, just 65. So if I put 65 in right here, 65 minus 15, this is actually equal to 50 degrees over here. So if that's 50 degrees, then I know that this one is also 50 degrees. I guess I can just say 50, but degree symbol's already on there. Okay, so same thing here. Again, if z is 65, then this is actually 65 times 2, which is 130. So x would be the same as that, and x would be equal to 130. Now, I always just double check to make sure that makes sense. These add to 180, so it looks good.